Good morning, everyone. I'm Alexander Vandekart, and I'm a student of TYBSc Mathematics at SIS College of Arts, Science and Commerce, Science West. And I would like to extend a warm welcome to all of you to this one-day webinar on pathways to develop research skills in mathematics. We are really glad that you guys have decided to join us on this beautiful day, and we hope that today's session would be very enlightening for you. To start things off, I would like to call upon our dearest Vice Principal and the RUSA coordinator of our college, Dr. Satish Sarfare, to give us the welcome note. Over to you, Satish, sir.
Yeah. Thank you, Alexander. I believe I am audible. Yeah.
Yes.
Namaskar and greetings from SIS College of Arts, Science and Commerce, Autonomous Science West, Mumbai. It gives me immense pleasure as a RUSA coordinator to welcome the invited speakers, faculty and students for the national webinar titled Pathways to Develop Research Skills in Mathematics, especially under the aegis of Rashtriya Uchchatar Shiksha Abhiyan. When I saw the list of invited speakers, to begin with, Dr. Sharad Sane, Adjunct Professor, Chennai Mathematical Institute, Chennai. Dr. Siddharth Gadge, Indian Institute of Science, Bangalore. Dr. Jyotsna Prajapat, Department of Mathematics, University of Mumbai. Dr. Rekha Santanam, Indian Institute of Technology, Bombay. Dr. Anisa Shorodwala, Indian Institute of Science, Education and Research, Pune. And just out of curiosity, I was going through their profile. I realized that one could not have asked for a heterogeneous mix of people who are from conventional and from contemporary areas as far as research in mathematics is concerned. I also take this opportunity to congratulate the Department of Mathematics, convener Professor Rekha Madam, and the faculty members of Mathematics Department. I am also glad and happy that uh, the former head Department of Mathematics, Asha Madam, is also there with us today. It's indeed nice to have Asha Madam with us. When it comes to research skills, whatever little bit of research which I have done, maybe I'm taking that as the premise for these opening remarks. That if everything around us is numbers, as I have read in terms of mathematics, and when I just got to know that the number of participants is going to be exceeding 140, I think it befitting the theme of today's national webinar. It indeed speaks for itself. It's also a coincidence that yesterday afternoon I gave a plaque courtesy Marathi Vidyan Parishad of Ramanujan sir to Rekha madam. I got the photo frame of Ramanujan sir. I was not knowing really that yesterday night Rekha madam will tell me that something like this is there and I'm supposed to take care in welcoming the dignitaries and the invited speakers. I am also welcoming you on behalf of Dr. Uma Shankar, Principal, SIS College, and my colleague Vice Principals. This kind of a workshop, if you ask me, is required in the form of a webinar. You call it as a workshop, because I believe that this will inculcate research aptitude among students, and more so with the kind of theme which is there, will develop research skills, not just from mathematics point of view, but it would also have an interdisciplinary approach. When I see that the invited speakers are from areas such as optimization problems or from industrial research and consultancy, it also reminds me of the fact that yes, mathematics is not just about numbers. When it comes to students, students are not just problem creators. I think this kind of a webinar today will also prove that students can be problem solvers in their own way. Before I close, I hope and pray that one of the peripheral outcomes of this kind of a webinar would be, with an illustrious line of speakers, that at least some of the students can think of pursuing research as one of the satisfying career options besides inculcating research aptitude. I think with these few words, uh, if I have taken more liberty, kindly pardon me for the same. Rekha madam, if you allow me to leave, because I have a TYBSc lecture, and I'm sure if I get time, I will be happy to join you back. Is that okay?
Yeah, it's fine. No
Yeah.
problem.
Thank you so much.
Okay, thank you, sir.
Um, yes, so thank you, Satish sir, for even being here in spite of you having a lecture. So thank you so much for coming here and addressing all the speakers. Now I would like to call upon our very own head of the mathematics department, Ms. Rekha Vadve Paratkar, to give us the concept note.
Thank you, Alexander. Our guest of honor, uh, Honorable Professor Sane, uh, all the distinguished faculty members, uh, Dr. Anisa, and many others, as well as all the participants and my dear colleagues. Uh, I am very happy to see you in such a large number. Now, let me just explain you why we decided to have this topic for this webinar. What has happened that nowadays, all as a faculty member, you know that NAC lays emphasis on research. Emphasis is more on research, and nowadays students are also going for higher studies in mathematics, and somewhere or the other they have to use some form of research, and they are also confused what is research exactly, because what has happened, there are so many seminars and webinars and conferences on research methodology, but research in mathematics is quite different from other subjects, because many times it is abstract in nature. So people get confused, exactly they don't know. There are so many bright students. Every year there are students who have inclination for research, but they are also confused exactly what to do, and someone should guide them. At the same time, they should get motivated for doing research activity, because people don't know much exactly what is research in mathematics. So we thought that we should have one webinar specially devoted to mathematics research, and so that idea materialized, and we got such eminent speakers here. So in this sessions, basically what we are going to do, first session will cover general idea about research. Honorable Sani sir will talk about the general research, how it changed from previous to this new times. Then the second session, various contemporary areas they will be covered, and the speaker is from very much active in research, and he is actually from statistics, but he has done research in mathematics. And third session will be mainly devoted for PhD related research and the queries, and last session is for panel discussion. In that all your general queries will be taken into account. At the same time, minor research, writing paper, projects, and all these things will be considered. So I feel that you will have some fruitful information, and you will have amazing sessions. So I won't take much of your time, because you are eager to hear these speakers. So now I will request my colleague Vaishali Farnikar to formally introduce Professor Sane. And namaskar to Sane, because he happens to be my teacher also. Thank you, and over to Vaishali.
Thank you, Rekha madam. Good morning, everybody. Respected guests, vice principals, dear colleagues and participants. We are fortunate to have with us Professor S.S. Sane as a keynote speaker for our webinar on research in mathematics. Sir was affiliated with University of Mumbai from 1982 to 2010 and then with IIT Bombay from 2010 to 2018. Our respected speaker has been an active researcher for several years. This is evident as he still till date published more than 70 research papers in various journals. He has collaborated with other mathematicians and has visited several countries for academic work. He has authored a textbook titled Combinatorial Techniques, published in TRIM series. His work on quasi-symmetric designs is published by Cambridge University Press in the London Mathematical Society lecture note series. He has held Commonwealth postdoctoral position in 1979 to 80. In 1985, he received Alexander von Humboldt Scholarship from Germany. In 1996, he was a recipient of Distinguished Alumnus Award of IIT Bombay. In the year 2003, University of Mumbai awarded him as the best teacher for the year. From 2005 to 2015, for 10 years, he was a nominated member of the Academic Council of Indira Gandhi Institute of Development Research at Mumbai. He was national coordinator of the Mathematics Olympiad program activity from 2009 to 2012. Currently, he is elected Fellow of Indian Academy of Sciences at Bangalore. At present, Sir is the adjunct faculty at Chennai Mathematical Institute. So, with this brief information, I invite Professor Sane to educate us on today's topic. We all are eager to listen to you, sir. Over to you, sir.
Okay. Can you hear me?
Yes, sir.
Yeah. Okay. Thank you very much for the invitation, as also rather lavish introduction is what I would say. Hope that whatever I'm going to say, it's slightly nebulous, but will make some sense to sizable number of people. Let me see if I can. I'm a little nervous here. I need to share a file. There should
Excuse
be.
me, sir. Can you switch on your video?
Okay, sure.
Yeah.
Yeah. You see me now. I need to share a file. How do I go about it?
Sir, is the file open in your laptop?
Yes, file is open on the laptop.
Then
Now,
you
there is an upward arrow on the right hand corner of your screen on top. In the screen of Teams, na? There is an upward arrow.
Next to the leave button, you will find a small upward arrow.
Next to the leave.
On the right hand side, top.
near between mic and leave button, there is
Oh, the
upward arrow.
mic. Okay.
So that upward arrow you click and you will
Yes.
find
Yes.
share.
I got it.
Yeah.
I think it should be.
So you should click at that, share the screen.
So you will get, sir, various options.
Yeah, you see the
Screen. Share screen. Entire screen.
And there you will find screen and share content. So you click at the screen.
Okay, 1 minute.
Or sir, if you could quickly mail it to one of us.
No, that's okay. So I think I should be able to manage this. This says that the share tray is open.
Yeah, so
okay,
screen.
Okay, I got.
Screen and window. So use.
Yes, sir. We can see your screen.
Oh, you can see my screen then. I'll just enlarge it. Yeah. Can you see it now?
Yes, sir.
Yeah. You can see.
Okay. Outset, I have to thank the SIS college organizers for organizing this event and inviting me, and also for rather lavish introduction. I hope I can somewhere prove equal to it. To the title that was given to me, I think I've added the second line, nurturing research skills in mathematics, also personal experiences and opinions. So let me begin with paying tributes to mathematics itself, importance of mathematics. Your vice principal did that, and let me second it. Yeah. Here is a quote from Giancarlo Rota, one of my very favorite authors, gifted English writer. For as long as we can reliably reach into the past, we find the development of mathematics intimately connected with the development of the whole of our civilization. For as long as we have a record of man's curiosity and quest for understanding, we find mathematics cultivated and cherished, practiced and taught. Throughout the ages, it has stood as an ultimate in rational thought and as a monument to man's desire to probe the working of his own mind. Rota was a prolific writer, published several books, and one of his students, who is extremely well known, combinatorics, Richard Stanley, was a plenary speaker in one of the ICMs. So this is how the course of the lecture is going to take place. Introduction and some reminiscences. In fact, the word reminiscences I would have to repeat. That term I would have to repeat several times, because on a topic like this, it's a subjective opinion, and therefore necessarily personal opinions will matter. It's just that not everyone will agree with it, but nevertheless I'll express it. Yeah, as I just said, I have to indulge in some rather personal reminiscences while talking on this important topic, and I presume that I can spend a few minutes on this. When I did my PhD at IIT Bombay long ago, this was way back in late 1970s, 78 to be precise, there was a sizably large number of PhD scholars in mathematics department at IIT Bombay. We were classified into two groups. I mean, this is strange, but that was the case. The pure mathematics group, to which I loosely belong because I did not do much of hardly any computations on a computer, and a large chunk of many others who were called applied mathematics group. Despite the fact that I did not do a great deal of pure mathematics then, and even now, I mean, I suppose all the other speakers will agree. I was classified as doing pure mathematics due to a certain activity the students working in applied mathematics indulged, and I did not do that. I mean, I did not do what they were doing. Therefore, I was not an applied mathematician. What happened was something like this. Most of the students who pursued PhD in applied mathematics, they had the following daily job assigned to them, which they carried out with utmost sincerity. They would use punch cards. Those days, punch cards was the only way in which you send the program into a computer. I mean, across the city of Mumbai. In fact, this was the case. Each card recording a single command. These were literally cards that could be punched with a proper punching machine. Each card recording a single instruction in Fortran and what was called BASIC those days. Applied mathematics research scholars would either have these cards processed in the computer science center of the institute itself, IIT Bombay, and that computer was very slow. It was gotten in IIT from Russia and was therefore extremely slow. Alternatively, they could, and that is what many of them did. They would use the faster method of making a trip to TIFR, also have some decent lunch in TIFR canteen, which was a rare thing if you lived in hostels. And they could boast about it. And that was a luxury for hostel students like me. And hand over the punch cards and get the results the next day. I used to feel rather jealous of applied mathematics people enjoying that luxury. Though they thought that people like me were just whiling away their time doing nothing, etc. And it was much later, after finishing my PhD, that I spent a larger time at the TIFR itself when I joined there as a postdoctoral fellow. Much water has flown over this issue of animosity, I mean, between pure and applied mathematics. This was quite visible in IIT Bombay those days. The last 30 years, 35 years or so, one of the major contributors for making the lines of distinction highly porous, so there is no wall now. There is no wall that separates pure math. There's no thick wall that separates pure mathematics from applied mathematics. And now you talk of various types of mathematics. And the main contribution here is that by computers. Computers have changed the world completely. The entire world is changed completely. How else does one explain the rise of branches like coding theory, information theory, cryptography, and many other branches that must be called applied mathematics now because they're useful to the society, but they also use very deep results from pure mathematics. Branches mentioned in the previous sentence, they have extensive applications in communication networks, electrical engineering, digital image processing, and even modern designs. Just to begin with, an elementary example, the ISBN code that we see on every published book these days is what is called the library of whatever it's called, the Library of Science Congress. They use them. They were using modulo relevant arithmetic. I'm told now that this is also changed. I mean, they use modulo 17 arithmetic. That's very interesting thing from extremely elementary number theory. Therefore, let me get into an actual puzzle type problem as a simple observation exercise. Okay, this is, I think this. Okay, let me describe before I show this. What has happened here is something like this. This will need a description. There are as many as n prisoners in a prison, and the jailer, the keeper of the prison, he decides something like this. He puts a hat on the head of every prisoner. It's either a red hat or a blue hat. They're all let off if they can guess the colors, all right. This doesn't appear to be a big deal. Only problem is that you cannot see color of your own hat. This is the whole problem. So looking at the colors of other hats, so every person, if there are n people, there are all the others you can see and guess the color of your own hat. And presuming that everything is equally likely in this world, there is no. If there is a scheme that the jailkeeper has, then they could have guessed it. The person, okay, there is a further rule here. Several people can decide to guess the color. It is, but at least one has to So those who don't get, excuse me. Sorry about the intermission. You're allowed to say pass here. That's perfectly all right. It's just that not everyone can say pass. So there is a certain number of people who don't say pass, guess the color of their hats, and if the answers are correct, then they are all let off. The prisoners can also discuss a scheme among themselves, not after the hats are put, but before the hats are put. A simple observation exercise, convince yourself that nothing better than a probability of half can be achieved. You cannot. So what you do is you just assign one of the two people. If there are two prisoners, one of them will guess, the other person will say pass, and if he says red with half probability, because there are only two colors, with half probability, both of them will be let off. With a half probability, they will not succeed. With three people, just with three people, we can achieve a higher success rate. Really speaking, so what you do is you make some people who give the answer, namely guessing the name, guessing the color of his her own hat. Whosoever opts for it, he has to guess the color of. There are as many as 2 cube 8 possibilities. By simple pigeonhole principle, two people must wear hats of the same color, say red. I mean, this is okay. If it is blue, we'll just flip the situation over. Suppose number 2 and number 3 are wearing red hats. This is what I've shown. And the question mark is for the first person to guess the color of his hat. If he chooses the question mark to be blue, then he fails only when all the three colors are red. And this is a scheme. This is quite a good scheme. Each prisoner, spelling mistake, each prisoner looks at the other two hats. If they have different colors, he says pass. So that is fine. If they, I'm sorry, if they have, this should be, if they have same colors, okay, this should be, okay. If they have same colors, he volunteers and declares the color of his hat. That word should be same, the second line. And declares the color of his hat to be the opposite color. Okay, that's exactly what we did the previous slide. And that question mark is settled to blue and not to red. We can then claim that this strategy will work with a higher percentage. In fact, if two persons are red and the other one is blue, the third is blue, the third person who sees the same color on the hats of the other two, he will guess and his guess will be correct. Exactly one person will then volunteer, others will say pass, and he'll also succeed. Of course, there is a failure possibility. The strategy will fail exactly when all the three hats are of red color. In that case, what will happen is, following the algorithm, the scheme that we devised, everyone will guess the color of his own hat to be blue, and that's an utter failure. But the thing is, I mean, they're not over punished. They're just sent back to gallows. They're just sent back to the prison. So every person will volunteer and will give a wrong answer. Fortunately, this can arise only in 2 out of 8 cases. This is the main point. So in conclusion, that strategy has a success rate of 3 upon 4, 3 over 4, which is higher than half. What will I do in case n is at least 4. Just keep one person permanently to keep shut and the other 3 people follow the strategy that we just devised, and you get a success rate of at least 3 upon 4. In fact, it can be shown that there is a strategy that as n tends to infinity with larger number of prisoners, the probability of success can be made arbitrarily close to 1. This is a big achievement. It's a huge achievement. From a simple-minded half, we move to 3/4, and then we can, with larger and larger number of prisoners, we can let this probability of success reach 1. Therefore, almost certainly they all will be let off. Okay, that gets me to the second section. What this is based on, I did not describe that. I mean, the assertion, this last assertion here, it can be shown that there is a strategy that as n tends to infinity, the probability of success can be made arbitrarily close to 1. This does require that the prisoners know some mathematics and quite a good deal of mathematics. I mean, this is based on what are called Hamming codes. This is just based on the idea of binary Hamming codes is what it is based on. It's a foolproof, it's quite a foolproof strategy because you have, with a very high success rate, the scheme is very clear. Hamming codes were, they were discovered by Hamming around 1950s, and in fact, this is the kind of forerunners of this is the beginning of the branch of mathematics that is now well established as coding theory, is what it is called. Probably more precisely, it should be called algebraic coding theory. This previous discussion tried to make clear the point that the distinction between pure and applied mathematics is fast vanishing. The entire thing, the previous slide also, it is just using modulo 2 arithmetic. It is nothing other than that. You construct right kinds of vector spaces over the field with 2 elements, right sizes, etc., and then you get what you want to achieve. Now have branches of mathematics such as applicable mathematics and even applied algebra, a large part of which is nothing but, I mean, lot of it is theoretical computer science. Interestingly, this fact about thinning the lines of separation also holds about some opposite titles such as discrete and continuous mathematics. And in fact, it's quite innovative person. An extremely good blending of discrete and continuous mathematics is to be found in a co-authored book called Concrete Mathematics. That's the name of the book. So this is one of the authors here is a father figure of modern computer science, Knuth. It's a 3-authored book. Concrete Mathematics is a very interesting book. Many good problems, extremely good exercises. How this blending has resulted in creating extremely nice computer science needs to be read from the choice of topics in this book. And Knuth's own life is a testimony to this fact. He began his career publishing extraordinarily good work, research papers in number theory. He began as a number theorist and was very successful there. Around 1960s, he turned his attention to theoretical computer science. And the result is for all of us to see. You probably know what I have typed here. What you see here is a PDF, the final outcome, the file that I'm showing to you. In fact, probably it is true for all the speakers. A PDF file will be shown. But before that, I did type LaTeX, the LaTeX file. So AMS Tech was a gift from Knuth to the American Mathematical Society. It was a free gift from Knuth to American Mathematical Society. That's the last sentence. The best and most prolific graph theorist today, Bolobas, had his PhD in He actually did PhD in functional analysis. I mean, quite a prolific author. One of his students, Tim Gowers, won Fields Medal, in fact. Okay, now some more things to come. You all know, I mean, most of you, I think at the undergraduate level, there is a probably even a compulsory course in graph theory. So graph is a pair for us, vertex edge set, edge joins a pair of vertices, complete graphs. Okay, that's a slide I don't have. A graph that can be drawn on the real plane without the edges crossing each other is called a planar graph. We wish to color the vertices of a graph, given graph G, in such a manner that adjacent vertices receive different colors. This is called coloring of G. The least number of colors necessary to color a graph is called its chromatic number. Make a slight detour here and study as to how a graph can be colored using greedy ideas. So let me label the vertices beginning from V1 through Vn in that order. Imagine as if you have a color box and where the colors are kept, and you take out a new color only when it is forced. Thus, having colored each one of V1, V2 through Vm, we examine all the neighbors of the next vertex that have already been colored and take out a new color only when it is really forced here. With this obvious stipulation, use the smallest number of colors, immediately see that this is a proper coloring. And this gives an upper bound on the chromatic number. Unfortunately and interestingly, typically for a graph theorist, you try to ask the question whether how far this is good. Now this does depend on that sequencing. This does depend on the sequencing, and there are as many as n factorial sequencings here. Therefore, if you choose a good sequencing, you would be lucky get the chromatic number. But that may not happen. And then joined with computer science, you try to guess how many times this kind of thing will fail. I mean, or even if it gives a bad answer, how bad it is. If the actual chromatic number is chi of G, maybe it produces an answer which is twice of that, which may be good enough, etc. This problem has attracted big attention in graph theory for the simple reason that this is generally believed to be true that it's NP complete. It's not even just NP complete, it's NP hard problem. That's the 4-color conjecture. Every planar graph, the chromatic number is at least 4. It is less than or equal to 4. 4-color conjecture was made almost now 125 years ago, and there is a long history of attempts to solve this seemingly easy problem. In fact, many incorrect claims were made in this regard, the most important of which was given by a gentleman named Kemp. He missed the proof, but he could only prove that 5 colors are sufficient. However, and interestingly, for 20 years, Kemp's proof remained unchallenged. So people did believe that Kemp has actually proved the 4-color conjecture. What he proved was that the chromatic number here is bounded by 5, and that is not what was asked for. 4-color conjecture, which is now called the 4-color theorem, was finally proved by researchers at Mathematics Department of University of Michigan in 1976. As a result, the Mathematics Department of University of Michigan proudly carried the following logo on its letterhead. So this is a logo on the letterhead. 4 colors suffice. The proof of 4-color theorem made use of arguments made by Kemp in a highly refined way. reducing the original problem, which permits one to have infinitely many possibilities to a problem with a very large, several hundred numbers of configurations of awfully large sizes, whose checking by hand would have taken some centuries. This was done by using a computer. A slightly better solution is now available on the internet. This is by uh, these two people who probably have the most seminal work in graph theory in last 100 years, Robertson and Seymour. Even these authors comment that they would be happy to see a reduction in the number of cases, and they would be even much happier if a tangible, purely mathematical proof could be provided. Computer proof of four-color theorem created ripples here, ripples on Earth, and lot of sensation because it was the very first proof of that kind. Absolutely a very first proof, because it's a statement in mathematics and you're trying to prove it using computers. The world was for more sensation to come in time to come. Let me describe something that is near my heart, something where that is closer to my own research work. A projective plane of order q bigger than or equal to 2 is an arrangement of q square plus q plus 1 points and equally many lines. These are subsets. Lines are just subsets of size q plus 1, equally many. Everything is symmetry here in such a manner that 2 points are commonly contained in a unique line and every 2 lines intersect in a unique point. A projective plane of order q can be constructed whenever q is a prime power. The converse is not known to be true. This prime power construction is pretty easy to work with. You just take that's what is generally called the projective geometry of 2 dimensions, because you have a field with q elements available when q is a prime power. The converse is not known to be true, very widely believed to be true. We do not have a projective plane of order 6, and this was known more than 100 years ago now. The first order of a projective plane where the existence was in doubt was 10. This was the first order. Through a lot of hard work with ideas involving coding theory, in fact, quite a deep coding theory is used actually, and many others, coding theory coupled with invariant theory, and many others, a group of mathematicians finally could come to the conclusion that there cannot exist a projective plane of order 10. The final shot on this problem was by mathematicians from Canada, who wrote elaborate programs and used 183 days of running time on the fastest known computer those days, Cray computer. But even the Cray computer required 183 days. And this was in 1980s. The researchers who gave computer proof have repeatedly opined. They repeatedly said this and appealed to the mathematical community that they would like to see a computer-free proof in their own life. But that has not happened so far. And it looks unlikely that it will happen in the future. Not in the near future. The second problem, namely the first problem, was that of planar graph coloring, projective plane of order 10, discussed on the previous slide, is certainly a problem from discrete mathematics. I mean, it's purely a problem in discrete mathematics, in the sense that someone with a super computing power should be able to solve it, since the question itself is finite, is that of checking finite number of but extremely large number of possibilities. The first problem is not quite that way. It's not quite finite, but it has a discrete flavor. A very large number of problems, both in continuous and discrete mathematics, have been solved in the last 25-30 years of worlds witnessing really high-speed computation. These include problems not just from discrete mathematics and algebra, but also from number theory, analysis, and topology. All right, moving on to the last few slides. What I'll say now and in the next few minutes is a collection of some stray thoughts. But since the talk is sufficiently verbose and lengthy, and on personal reminiscences, I recall the time my mother is no more. She passed away almost 15, 20 years ago. But she knew, we thought that she was clever enough in knowing how to take advantage of her age. I mean, now I belong to that category. So I can take some advantage of the age. I expect that some people in the audience may believe that there is a fair amount of content in what I say. To say the least, most of it is from personal experience. Choosing a right topic for research work is to an extent a matter of luck, as also a function of right temperament on the part of both the advisor and the student. And I will not dwell much into this because that will lead to too much of personal experiences, and I would like to avoid it as far as I can. This was also alluded to in a talk that the Nobel Prize winner Venki Ramakrishnan gave at IIT Bombay a few years ago. And in fact, he did say that choosing a right topic uh, is quite important. This question was asked at IIT Bombay to him. The talk probably was around 2014-15, around the time, about a year when he got the Nobel Prize. That applies even more so to an abstract topic like mathematics. Advisor does play a major role here, or is at least expected of him or her. How far that is true, something, it's a subjective matter. Publication in a good journal is a boost to the researcher, but good journals usually take a long time to process. I mean, the time taken now is even much longer than what it used to be when I did my PhD. And in fact, this must be around 1977 or 78 that the first time I wrote a single author paper, uh, I sent it to the rules prevalent, those in IIT Bombay those days, was that you don't send a covering letter with the research paper. And therefore, the covering letter had to be sent separately. So you send two letters, one the covering letter itself and the other one the paper itself. So this was about a 15-page paper that I sent to a person, German mathematician Strambach. He was the chief editor of Geometry at Educata. And I received in a few days, I received a reply from him saying that he received the envelope, but there was no covering letter. And he presumed that it is for publication in Geometry at Educata and has already turned it to a referee. Now, this is quite a matter of luck. I mean, he could have just thrown it to dustbin. It's perfectly possible that he could have just thrown it to dustbin because there is no covering letter. But those were the rules prevalent in IIT Bombay those days. This was to save some postage. And fortunately, the paper got accepted in a month or two. You cannot expect that kind of luck these days. As the slide is showing, publication in a good journal is a boost to the researcher, but good journals usually take a long time to process your paper. Almost all the people who are going to speak today will agree with me that a referee job is a thankless honorary work, which some people take very seriously as a part of professional obligation. I mean, but not everyone does. Thus, most of the good journals face shortage of referees. Compared to the time when I finished my PhD way back in 78, there is a lot more rush for publication. And this has given rise to even unethical practices in terms of spurious and what is a standard term here is predator journals. And we all get lots of spurious emails these days. I mean, in the world of over information. Second problem is narrow specializations. These are becoming so common in mathematics that a person working in any area hardly has any idea of what is going on outside of his area. The paper publishing racket has assumed such an ugly form across the world that there is a rat race for publication, good, bad, or ugly, anything. This reminded me of an anecdote that I feel like sharing with all of you. When I appeared for a professor promotion interview at Mumbai University in somewhere in 1980s, probably 85 or 85. An expert knew that I work in design theory. Since graph theory is an allied combinatorial area, graph theory is certainly like a brother or sister of design theory. The expert also worked, he also worked in graph theory, uh, fairly known name in Indian Statistical Institute circles. He asked me with an air of expectation as to which mathematics will supplement my own research work. And those days, whatever I was working with, I instantly answered number theory. And I understood later that this graph theorist was not very happy with my answer. Though I did get the promotion. I mean, good part there was I, I got the promotions. The punchline is more you know, the better it is. And that's the thing. I mean, not only I should know graph theory, but I should also know a good deal of number theory. Most universities, including Mumbai University, now have a paper named research methodology. I think this was mentioned by Rekha Vatve in the opening remarks, or some similar sounding term. Since this was devised by people, and, and this whole idea of research methodology was devised by people working in social sciences and humanities, it is not of much help to mathematics. It mainly focuses on how to write bibliography or list of references. I mean, that you write in alphabetical order, how to alphabetically organize references and such similar things. That does not help much a topic like mathematics. Some years ago, Mumbai University did, I don't know whether this still exists. It had come up with a so-called novel idea of making it compulsory for a PhD candidate, or maybe it was a rule across Maharashtra. PhD candidate to declare the methods he is going to use in his research project. This is downright unjust for a topic like mathematics. Some of you would, let me share this story with you, would know that Andrew Wiles, who is now credited with having proved Fermat's last theorem, FLT, he did not wish the world to know that he is following a certain line of attack on Fermat's last theorem. So he wanted to keep the mathematicians in dark that he's working on this problem, just to make sure that mathematical community is kept in dark about his pursuit. He kept publishing research papers in number theory of a fairly high standing, but not connected with Fermat's last theorem. Even and then finally he published the proof of Fermat's last theorem was published. Even the final proof that Wiles gave had a big gap in the proof, which was fixed almost more than a year later. Though Wiles was about to give up the claim on having proved Fermat's last theorem. So on this background, I mean, if you look at this, if you declare your line of working for a mathematical research work, it's pretty unfair to a candidate who just begins his research work. I don't know if the rule still exists in Maharashtra or Mumbai University. Some people who do mathematics are extremely good problem solvers, and some are very competent theorizers. A good example of the former, the problem solver, was that of Paul Erdos, and it's more than 1,000 papers to his credit. While the latter, I would say, was Wiener. Wiener was a big theorizer Wiener worked on the foundations of stochastic processes. Erdos was a great problem solver, publishing more than 1,000 papers and worked in diverse areas such as number theory, combinatorics, and analysis. Erdos also declared a large number of cash prizes for solving his problems. Personally, I have great liking for Erdos's work. I mean, this is subjective opinion. Since I have also worked on with some little success on one of his problems. In this direction, it's a nice idea to evaluate contributions of mathematical Olympiad activity to fostering quality mathematical research work. This was not considered to be the case. Most eminent mathematicians downplayed and even belittled the role of mathematical Olympiads. But now if you take a cursory look at the winners of Fields Medal recipients of the International Mathematical Union, the IMU, and the Lifelong Achievement prestigious Abel Prize given by the Norwegian Academy, this is a pointer in the exactly in the opposite direction. Most notable example here is that of Loas. He was last year's Abel Prize winner for his outstanding work in theoretical computer science. In fact, that award last year was shared by two people, both of them working in theoretical computer science. One was Loas, the other was Israeli mathematician Wigderson. Incidentally, Loas was also the president of the International Congress of Mathematics, the ICM, held at Hyderabad in 2010. Concluding the topic of theory versus problem solving. This is always a debate that will go on forever. I'll only mention two biographies. In fact, since I mentioned two names, I should mention two biographies. Uh, Paul Erdos by Hoffman, the man who only loved numbers, and Wiener's biography is very well written book by Pesi Masani. In fact, his earlier career was at Bombay. It was with Bombay University. The final things, I want to be a mathematician and automathography. It's a very nicely written account of mathematics teaching and research by the prolific writer Paul Helmos. A second reference is that of 10 lessons I wish I had been taught by someone who had, this was the first slide that I showed, gifted and equally prolific mathematical expositor Rota, Giancarlo Rota. These 10 lessons are incidentally available on the internet. This is, I mean, just click 10 lessons by Rota, you'll get that. Rota even gives instructions on how to give good talks. Don't speak on several things in one lecture because the audience is like a flock of sheep that will run away helter-skelter if you talk on several topics in a short time, and then no one will pay attention. Rota even talks of wiping off the blackboard properly. I mean, probably there are no blackboards these days, but the Chennai Mathematical Institute incidentally does have big blackboards. So this was the case also in IIT Bombay, without leaving any spots. He also talks about how to avoid giving bombastic titles for the talks or research papers, and the need to give adequate credit to researchers who have already worked on the problem. Thank you very much.
Um, yes, sir. So are you done with your session?
Yes.
Okay. So thank you so much, sir, for this wonderful session. Now we'll be opening up for questions. So to all the audience and participants, if you have any questions, please either put them in the chat box or you can raise your hand. So as and when we call your name, you can just present your questions to sir directly.
Uh, Sane sir, I think you
Yes.
can stop sharing the screen and you may look at the chat because one person has already asked a question, one student. So
Yes.
otherwise we
Yes,
will,
I can
yeah,
see the chat.
yeah, then you please.
Uh,
May I read the question for you, sir?
no, I think I should be able to do that. Show conversation. Yes, I see. Yes. Well, Siddharth Gadgil, thanks. Okay. Well, okay. I've heard from people. Okay. I've heard from people that mathematical research does not provide much money. So to ensure, would you please shed some light on ways to earn money with research as my main occupation? That's a good question. I say one way of answering this, I suppose, is you will agree that it's not completely true. Uh, I mean, in fact, now you see people who actually pass from the best known IITs in India, Bombay IIT, Madras IIT, Kanpur IIT, etc., the BTech students, they finally take up to teaching mathematics. Okay. I know of umpteen cases of this kind. Uh, and probably the classes like brilliant classes or PACE Academy or whatever, they're full with mathematics teachers who have degrees in engineering. Okay. So that partly should answer your question. Uh, on the other hand, on a personal level, uh, I can only say that I was provided adequate training when I taught, and with passion I could enjoy it, and that's all. That is what I could say. The right kinds of places here are places like Indian Statistical Institute. Uh, Probably the second speaker, Professor Siddharth Gadgil, would be a good person to answer that question. Uh, But on the other hand, let me tell you, these lines are getting blurred completely. I mean, uh, there is a person I know, a PhD from TIFR, who is employed with Credit Suisse company now, okay, for last several years, and with a good PhD in topology. I suppose that does answer your question, but it's a more detailed thing would be little more difficult. This is quite true about mathematics and statistics also. It's not true that all these walls are really quite thin now. They're not that you work in such and such area. I mean, uh, this was the case, I mean, several decades ago. It's not quite the thing. On the other hand, you need to do some quality work. And this is a difficult question. Yeah. Okay. The one question is, how does one pursue mathematics while living in Mumbai, which isn't exactly friendly for academics with its high commuting times of 2 to 4 hours? I mean, that's also little personal question. It's not just probably in Mumbai. This is quite true in all metropolitan cities. I mean, Mumbai probably leads this whole thing, but probably this also true in Bangalore. It's also true in Delhi, and Delhi traffic jams are horrible, is what I'm told. Though I have no personal experience about it. Uh, this is a much larger question. I mean, it's a more social question, and difficult to answer that.
Has anyone raised the hand? Please unmute yourself and ask directly.
How much time per week does one need to give at bare minimum to pursue maths? uh, I suppose you need to, if you want to doggedly work on something, you do need to spend quite a bit of time. not just pursue mathematics at research level, but even teaching mathematics, it does consume quite a lot of my time. I mean, it does consume for me. Okay. I would not, I mean, even a single course that I teach at Chennai Mathematical Institute does take quite a bit of my time. If I have to, if I think that I have done justice to the topic, because you see, students at Chennai Mathematical Institute are reasonably good. Many of them are quite good. Therefore, you cannot just do elementary stuff and get away with it. But this does depend. I mean, one has to have fair amount of involvement with the topic. The word for that term is passion. After PhD, what is process to get research and what exactly we have to do in research and curriculum about that?
I think there is a hand raised by
Hand raised.
Vijay
So,
Singh Chauhan.
yeah,
Mr. Vijay Singh Chauhan, could you unmute and speak, please? Ask your question.
yeah, go ahead.
Sir, why do journals take long time to process these days, in spite of relatively good resources such as technology?
I completely agree. I mean, I completely agree with you. I mean, the 1970s when I did my PhD, the resources available were, I mean, across the world, research, not so many research resources were available. I mean, it's not just in India that telephone lines were bad, etc. But even in America in 1980s, to make a long distance call, you, you had to time yourself, and this was the case even in United States. I mean, because the calls were cheaper if you if you actually phone at odd times, etc. So it's not that where I mean even when I finished my PhD, Xeroxing facilities were just not there they're not there in India at all. Even 1978 when I finished my PhD, my own PhD thesis was actually done on a cyclostyling paper. Okay, this had to be. I mean, I'm not really boasting about it. This was true for everybody. Everybody would. And IIT Bombay those days, if you wanted to copy something, you had to go to chemistry department, and there was something that they call ammonia print. Okay, which would make a very bad copy. It would make a pretty bad dark copy, and you had to be content with it. But within a few years, situation changed, and by mid 80s, 85, 86, Xerox machines were available across India, and they started becoming available across India. So, on the other hand, number of journals has increased. What should be? I mean, we're in more aspirational society. Uh, Therefore, everyone wants to be rich, and some people do manage it.
Okay. There are three more questions, one by
Yes.
Rahul Yadav, Sanab Ganesh Tulsiram, and Brishali. I believe these questions will be covered in our panel discussion that we are going to have
Okay.
at the end of the day. So, sir, with your permission, could we skip these questions? They're basically
Sure.
about
Sure.
how to go about PhD and research work. And we have a panel discussion for this.
Sure. Yeah.
So, any more questions from the teachers, faculty members?
Hello.
Yeah.
Yeah.
Uh,
So
Yeah. I just wanted to say hello to Sane sir, and it was nice to see
so
him after so
who
long.
who is that?
Jyotsna ma'am, please
Oh, okay,
switch on
Jyotsna.
your video.
Okay.
No, it is fine. I will
No, no,
not.
no, otherwise.
Uh,
We have Dr. Jyotsna Prajapat from Mumbai
so,
University.
yeah. I have to thank SIS College for bringing together so many people that I was connected with. Okay, so Jyotsna is certainly one person, and in the afternoon you have Rekha Santanam, was probably a student of this college, I suppose so.
Yeah.
Uh,
She's our
uh,
student. Yeah.
and was a colleague in an IIT Bombay for 8 years. So I have known Rekha Santanam for quite a long time, even as a family.
Oh.
Okay, so
I think Geeta, then we shall proceed
okay,
with our.
please go ahead. Yeah,
Yeah.
thank you.
Thank you, sir. Geeta,
Yes,
please.
Rekha. Yes, Rekha, ma'am. So that was quite an enlightening session, setting the tone of this webinar, which focuses on pathways to developing research skills in mathematics. Sir, I'm a student of Mumbai University, though I have never got the opportunity to be a student or taught by Sane sir. Most of my senior and junior colleagues are his past students, and I have always heard them talking very fondly about sir and his teaching ability. I'm really glad that today I got a chance to hear sir. So began with a trip down the memory lane. He took us to TIFR and IIT way back 35 years probably. And the card punching era, I think the participants of this webinar who are below 50 today may have never used the cards or punch cards or card punching machines. So that was really very nostalgic. He also explained how.
Let me add a line here.
Yes, sir.
It was a good homecoming for me. I left Bombay now almost 4 years ago. So and I left
Great.
Mumbai city 4 years ago. So this is
Okay.
a big homecoming. Thank you very much for it. Yeah.
Great. So you also explained how pure and applied mathematics, computer science, they used to be separate compartmentalized branches of study. And from there, you walked us to today's era where partitions, in your words, are thinning and diminishing. Partitions between pure and applied mathematics are vanishing. Sir emphasized the importance of mathematical thinking, thinking logically with reasoning, and to be able to solve problems through a very effective example of prisoner's hat problem. He has also suggested some reading material. We'll come to it in the end. Sir has very effectively explained the interdependence of allied fields like graph theory, coding theory, the use of computer programs in proving mathematical results, which is slightly new to a few of us. Nowadays, we see more and more students are attracted towards computer science, IT, data science, and they believe that is the future. So we, as teachers, I think teachers present here in this forum would agree with me that we get a very small intake, student intake, and most of them are interested in pursuing either statistics or data science or computer science. Very few students are really interested in pursuing mathematics, and today's webinar actually focuses on how to inculcate right skill sets among them and make them realize that yes, mathematics is the basis for all these allied fields that you would like to take up in future. Sir, I'm sure your lecture has enlightened all of us, especially the students present here today, that rigorous mathematical background is essential in order to take up research work in not only mathematics, but also in the collaborative and interdisciplinary research areas. Sir also commented on importance of choosing right research topic, the hardships in finding a good journal. So the reading material that you've suggested, I'm sure it's going to be very interesting to all of us to discover those books, particularly the biographies of Erdos and Weiner. I want to be a mathematician, 10 lessons. I've just noted down and I'm going to share it with my students. So on behalf of all the participants present here and the organizing committee, sir, I would like to thank you. We are all grateful to you for spending your valuable time in guiding us in nurturing the research skills among students. And sir, you mentioned in your speech about age, and you proved through your lecture that we are all mathematics disciples and age is just a number for us. With that, sir, I won't take too much time of everyone. Thank you very much once again on behalf of everyone.
Thank you.
Over to you, Alexander.
Um, yes, thank you, ma'am. Thank you, sir. So now we'll be having a short break before the next session, and we'll be starting the next session at 12 exactly. So if the participants want to just freshen up,